Okay. And then second is a remote sensing, that is sensing the object without physical contact with the objects. Third is a photogrammetry, that is stereo, that deals with the position and the shape of the Earth surface. Like you have a 3D surface, a digital elevation model, or the elevation as a third dimension in the Earth, on the Earth. And the fourth is cartography. It is a science and art of designing the maps. So what you produce is presented to the user in the form of maps, and you might be seeing those maps in the Survey of India, topo sheets, or many thematic maps from the agriculture, from forest, and from water resource department, and from the urban development department for the city developments, and then urban plans. All those things, maps comes under the cartography. The next is global position systems, that is GPS. It is a system of navigation satellites, which is about 20,000 kilometers above the Earth's surface, which gives the location and the time of the particular position on the Earth. And last is the spatial decision support systems. That is the integrated system. Sorry. Integrated system of many branches comes together that produce informed decisions. So you can based on the DSS, you can make a decisions for your area of interest. Today we will talk about some geographical information systems and remote sensing, and then global position systems. GIS. This is just an overview. What we are going to learn: GIS, need of GIS. What are the components, why it is been rise or been now used in many applications, basic concept and few functions, files and database, as well as some software, that is ArcGIS, as well as QGIS, and then application of GIS. In this I'm going to some basic things that help you to understand the basic coordinate system of the GIS. Here, let me draw the pen. Okay. So this yellow sphere is nothing, and with the lines on it, those are called the latitudes. So these, if you say that in XY coordinate systems, it is basically your x-axis. So this is a latitude is always the x-axis, and in your basic schools also you might be learn about equators. That is where the starts with the 0, and then if you go towards up, that is it is a north pole, and if it is go down to the equator, it is a south. So these horizontal lines are called the latitude. And the next blue is a longitude. These are the y-axis of on the Earth. These are not defined on the Earth's surface, but these are the imaginary things to measure the location on the Earth. So longitudes, you might be knowing the prime meridian, which goes from the London Greenwich Mean Time. It is a 0 there. And if you go toward the east, that is toward our India side and the Asia side, it is always east. And if you go to the Canada and American side, then it is the west. So these are the notation that you must learn. Towards right of the prime meridian is easting, and towards left of the prime meridian is the west, W, and towards north pole, it is always denoted as the north, and then down it is south. So combination of these two becomes the XY grid, that is called the Earth grid, which gives the position on the Earth in the form of latitude and longitude. If you see here, you might be knowing this 55 degree, 30 minutes and 00 seconds. This is a north, 60 degrees, 00 minutes and 00 seconds east. So this is basically on the northern hemisphere, as well as eastern side of your Greenwich Mean Times. So, and these angles are in degree decimals. So these are not a physical measurement that we see on the Earth, but these are the measurement on the Earth, spherical measurement on the Earth. which used to locate the position on the Earth surface. But if you see here, our Earth is not a regular fashion like we see in the pictures here, but it is an irregular shape. It has some many undulation like Mount Everest, and then Himalayan regions, then Satpura, then Sahyadri. So there are many hills regions are there. These are hills are known as elevations or actual shape of the Earth. So what we see on the actual is like you are seeing the rotating expression, and these geodesy is defined the study of the shape as well as the area on the Earth. So when it calls the Z dimension, that is the elevation, then it's become the geodesy. So it is always remember the Earth is measured into latitude, longitude, and the Z as elevations. If I have to define what is the GIS, it is very simple. It's a G stand for geography. So you know the geography means where something and what is at a given locations measured in degree, minute, seconds. So what we see the degree, minute, seconds is the location, that is a geographic. And then second is a stands for the informations. So what it indicates at that particular locations. With the locations, you may not know the description of that object, but when you have information of that location, then you can know what is the information about that place. So that information stands for I, and S for the stands, because it deals with the many systems that we are going to study, and GS for the stand for the system. So it's a geographical information systems. Remember, not geographic information, but geographical information system. So it is that system which helps in locations. So now the location here in GIS generally or in the geospatial community, location is always referred as a spatial. Spatial is always referred as a location of that object. And there is one more term, the non-spatial. Non-spatial means a descriptive information that I will learn. And these informations, that is your spatial information and non-spatial information, can be mapped, manipulated, and present to the end user. And typically it involves what? So what is that facility or feature or object on the Earth? If you have a schools, then you can term it as a school. But when you know that it is schools, once you go and verify that it is a school, otherwise it's just a building, one building, constructed building, just like a wildlife sanctuaries or your cities. So you know that there is a city, but if you are to define that what is the city, then you must have a non-descriptive information of that. The second is where, the address, the coordinator. So what and where. So it gives a coordinate or a geolocation of that particular object. Then it becomes a relationship, connectivity and proximity. You must be knowing that if there is a big stadium, then you must be seeing a circular round or circular shape that says the connectivity and proximity. Using the connections of proximity and connectivity, you can define the relationship of those things. And then fourth, an important one is what if. So based on those three things, you can you can model the scenario of the future by generating the future scenario and visualizing the impact of that scenario today, so that you can take the appropriate steps. So what if scenario can be generated and visualized at today's time for the future, and it helps in deciding the many decision makings. So it captures, store, update, manipulate, analyze, and display all form of geographical reference information. So geographical information means location information. It is referred and it captured, stored, update, manipulate, displayed, analysis. So all things can be combined into the geographical information system. So why it is rising? because there are many revolution happens in the information technology. First is a computer technology, processing network, users of computer, remote sensing. Number of satellites has now been increasing. The data now reception is very open. There are many open source data is also available. A global position systems. Earlier, these GPS were not available for the general users, but now these are being made available after 1980s. These are available, and therefore these are helping to become a common technology in the in our daily life. Communication technology, the server, internet, cloud computing. So these are actually helping factors or kind of drivers to give a rise to the GIS. The second is enhanced functionality of the software and its user friendliness. Because earlier the GIS were not where they're user friendly, like as you see today, Windows pop-up systems. Earlier those were in the command line prompt, and you have to remember the command and type the command, and then it will be executed, that particular function. So it will be hidden. So that whole things will not be available in front of you. This is not the case in today's world. It is more of the user friendly. Everything you can see on your screens and can judge what it does also. So those things are available. Third is visualization impact of GIS is now more. If you see, people don't like a big theories or big narration of sentence. They want a simple picture which can give it, which can show the exact description of that area or exact description of what they want. So pictures always says more word than the letters or the your words. So that is the reason these maps are also become popular. The next is geographical feature and data disseminate is now our everyday lives. We might be you might be using your Ola, Uber, or some food delivery apps, or even Google Earth or Bhuvan applications, or Survey of India maps. Those are now, it is your everyday parts. You have to depend on that. Wherever you want to go, you will just search your locations and drive to that locations. So it is that become our everyday lives now. And then many scientific research and scenario is possible using GIS, and those are the real world. So these are some of the factors that is given rise to the GIS. So need of GIS. So picture carries a lot of meaning. So information has geographical locations and locational data. So if you see the information of today, 80% of data is having some kind of a geographical location or geo tag or geo coordinates, and this helps us to become useful for displaying and analyzing the data, making spatial analysis and easy to for planning and monitoring and management assets as well as resource and systems. You can assimilate different source of data. Earlier, those were not the facility available in the GIS. Now you can bring out your own data from various servers, SQL, Oracle, all kind of data you can fetch, or your MDB or Access database or Excel dataset or TXT files. These can be bring into the GIS now and helping us to more meaningful analysis. The visualization impact, it carries a lot of, because it gives the monitoring and progress indication also of a projects, like a road projects. If you see the road projects in the National Highway Authority of India, NHAI, they don't have to go to entire stretch of the road. They can monitor using this GIS, daily progress and monitoring where it is, where and what it's happening. It has an analytical capability. So you can have measurements as well as scenario developments. So what ifs can be answered using this analytical capability. And you can share that information with many stakeholders now. So, that is a good thing about that. Now, what are the five components of the GIS? The first is your software. Second is the data. third is method, fourth is the people, and the hardware. So these are the 5 components of GIS where the entire system of geographical information systems work. Now we'll detail about those things. A software is nothing but a few kind of a set of series of functions or the instruction that executed. And these softwares are various kind of software. First is GIS software, or it may be database software, operating system, or network software. So these softwares help us to give a applications to GIS. So you do know any kind of GIS application or software that you can answer yourself. The data, the second most important after the software is the data. Without data, this GIS can't do anything. So one of the most important component of GIS is the accurate data. And those data are fall into different categories. The first one is a vector data. Vector data is in the point, line, and polygon features. Those we will learn. Just remember, range station, land parcel, buildings can be a vector data. Raster, those are the satellite image, or your DM, or your survey of India topo sheets. Scan topo sheets, images. Scan topo sheets, survey of India maps. Attributes, and their number of stations, rainfall, weather station data. So year-wise, you have a series of rainfall stations. So those can be attributed as attributes to the vector data. The third is a method. Once you have the software and data, then you must have a method, that is how it is going to capture, how it is going to store, how it is going to retrieve. So all those things are required here. The guidelines, some image specification, cloud banding, specification parameter, like you need to specify where the parameter of bands, DN value, vector deceleration parameter. So all those things are required in the specification standard. You may be having some project data requirements. So those standards can be embedded or clubbed into the this method. And then procedure, how you are going to capture the data, stored, and build a topology on it, and retrieve and make analysis. And the next one is the people, that is human resource. Once you have all those things, these can be helped by many. This system can do anything. So it needs a people. So what are the different kind of people that generally this GIS industry uses? The first is administrator, manager, GIS technicians, application experts, end user, and consumers. So these are the users of the systems. And the last one is the hardware. You must have a hardware to display the result, display the scenario, print the scenario, and print the maps and all the things. So these hardwares is the last component of the GIS system. So once you have this, all the components of GIS, so let us consider about the basic concept of GIS. So those were the components. Now we learn about the concept of GIS. So fundamentally, or ideally, there are only 2 types of spatial model. One is called the vector, and second is called the raster model. These are called sometimes model or sometimes a data. So if you see here, this data is represented in the points. So points in the form of polygon, it's a single coordinates, X, Y, just a single coordinates. It can be poles, manhole, site, or events, or any one single events of your, like a city, one city coordinates X, Y is Pune, or your say Mumbai, or Nashik, or Aurangabad. So these are the single point, and it has a X, Y coordinates. The second is a line. So it has a roads, stream, rail, and contour. So these are the linearly connected points. So linear feature is always digitized or stored in the form of lines. And these lines are a series of XY connected points. So this is a XY connected points. And this is a single point XY. And when the series of XY points connected each other, then it becomes line. The third is the area, that is a polygon. where you need to have give a jurisdictions, a area, just like your district, taluka, state, nation, country, world. So those are the areas, and these are polygons defined by the set of lines. And in polygon, always remember the start and end coordinates are same. So it is a closed polygon. So start and end is always closed polygons. Now, you must remember GIS, these three types of geometry can be stored in GIS: point, line, and polygon. Only three types of geometry in the form of vector data. Now, the next is a raster. So raster, what is raster? Is satellite images or even photographs. Your camera photograph or the your mobile photographs. These are nothing but the rasters. If you zoom it more at a pixel size, then you can see a circular shape, and that circular shape, individual shape, is a one unit, and that unit is called the single cell or grid or pixels. These are called these things. Now, how it can be represent the point, line, and polygon in the raster? If you see here, these single dot given on the piece. A single dot means one cell size or the cell. This is a point for the representation in the raster. So you can represent that in a vector format, or you can represent the raster formats. A line features, these are connected cells. So it is a line. And these are the polygon features, where all the polygons are connected, or the cells are connected and form the uniform polygons. So these, how it can be represented into vector and raster. We'll see in details those things. And raster also has a black and white as well as color images that we learn. And the number that we store is known as a digital number. You always remember these digital numbers are the number that is stored in the pixels is known as a digital number. Now, when you have a two type, then let's make another way of describing the vector and rasters. Here, a point, a line, a drainage, or polygons like a land parcel. And the same representation, if you want to make, it can look like exactly this way. A point is grid or matrix of rows and columns. A raster, you can say a matrix of rows or columns, or a series of X and Y coordinates in the form of cell or grid cell. So those cells are represented here, 1 point, 2 point, 3 points, and the connected cell as a line, and the polygon as a group of cells. And these rasters are generally used for the satellite images or the digital elevation models. So now, when you have to make a real world, then you combine the two things together, raster as well as vectors. Because raster has some different meaning and representation, and vector has a different meaning and representations of the real world. And that both together makes the real world. So here how it is mentioned in the GIS is a point, line, polygon as a vector format, and the raster in the form of images or elevation data, or in satellite images or photographs. Now here a little about that. Vector has a direction as well as magnitude. Always remember, and it is having a one file geometry. So if you create a one line geometry, you cannot store as a point, then it should accommodate only the line. If it is a point, then it can accommodate only the point. It will not accommodate polygon, either polygon or a line. Vector data can be represented as a point, line, polygon. And these points are measured and stored, and it has no dimensions. Point has no dimensions. Line data has measured and stored in the centimeter, meter, kilometer, and so on. Polygon data measured in the square centimeter, square meter, or square kilometer. It can be stored, relate, join queries and multiple table with the RDBMS also. RDBMS is a relational database management system. So these can be clubbed with the various systems. Only vector data can be query or join with the various relational database management system. Apart from vector, rasters is a matrix of rows and columns, and each unit is known as a pixel and grid or cell. It's a both cell, pixel, grid. A pixel is also known as a picture element. So the short form of picture element is a pixel. And grid cell. The image data is always stored in the square and rectangular shape. Always remember, it cannot store in the zigzag format. It's always stored in the square or rectangular shape. It cannot store in the polygon, trapezoidal, nothing. They are just stored in the form of square and rectangles. The image smallest unit is known as a pixel, grid, or cells, and the value stored in each pixel is known as a digital number. So what we see as a brightness of that is the digital number. And it can store only a single value, that is numeric value. Then basic concept, this is one more example how real world and other things can be seen. You can see here the raster image, and then same thing if you had to represent in the vector format, a point, a line, and trees can be represented. These raster representations, one is house here, and then river. You can see this is river, and this is a tree, a group of tree connected, and then one house. This is how the raster representation is. And the coordinate is always starts from the top left corner. So it starts from the top. Whereas if you want to see the vector representation of those images, then you can see here, it is a single point, a line, and polygon. These three geometry together becomes a vector representations of the real world. And the coordinates always starts from the bottom left coordinate systems. So coordinate always starts from bottom left. So this is the difference of raster and vectors representations. You can see here. And apart from the vector and raster, you can have a point where it is a dimensionless, a line which is the same things, a two-dimensional, it has a length and as well as width. You can see highways and roads and other things. However, it is to be mentioned here, the nodes and the vertices. The line always, and the shape of the line is always depends on the number of vertices on the line. If you see here, the number of vertices has increased and therefore the shape is curved. If it is a straight line, then you have only one vertices and second vertices. And the node. Node is a start and end node where the major junction happens in the line features. When in terms of polygon, it's a three-dimensional. It has area, perimeter, and boundary. Sometimes it is called the land use or land parcels or the area of districts or taluka or polygons. And these features are stored using the coordinate systems that is known as a map scale. So we'll learn about those map scale in the next few slides. These are some merits and demerit. Vector data requires very less storage. You can build the relationship of various data set with the vector model very easily. A ground output is very resemble like a hand draws, and it is very resemble like your actual situations. Spatial analysis is very fast. Overlay analysis, hierarchy analysis, spatial analysis are very fast in the vector formats. Demerits are more complex data structures. So you need to have a more structures. It requires more software and hardware, expensive, and some special analysis procedures are required to be difficult, like a kringing and all those things are difficult in the vector data model. And overlay and multiplying vectors often is time consuming. So if you see here the Bhuvan and other things, when you open a map, then there are many layers open simultaneously, and they comes one by one on top of it. So that it takes time because of the memory size as well as a number of complexity that is involved into vector data. However, in raster data model, these are like your rainfall, elevation, temperature, and runoff. These, if you see here, a coordinate systems where the polygons are represent, and The same thing here. Mostly it is for the continuous surface. Like raster data is mostly used for the continuous surface, means where the phenomena change in every few meter. Phenomena change every few meter, like a temperature. Temperature change keep changes every few meter. So, and it's continuous. The examples of this raster is your scan photos, digital elevation model, a DM, tin, and the grids. We'll learn with those things about raster data. It is stored in the raster formats, and the data stored in the each pixel is called the brightness value or the DN value or radiometric intensity. So all three things are together, and the pixel values is always stored in the comma 0 to 255. So computer can store only up to 0 to 255 values. So you see the pixels here, multi-spectral thick band false color composite image, and one single band high resolution images. And then the next one is here. You can see here, higher the value, more the brightness. Higher the value, more the brightness, and lower the value, the darker the pixels. And this is why the intensity of the pixels becomes important, and with the brightness you can analyze those images. Apart from the single 8-bit, there are different radiometric resolution also. Like you have a 8-bit, 16-bit, 32-bit, and it can be signed or unsigned. So 8-bit is 2 raised to power 8, 2 raised to power 16, and 2 raised to power 32. So these number of level of information it can store. And mostly remote sensing data, 8-bit or 16-bit data are available. Then raster data can have a code like a homogeneous. If you see here, if you have land use land cover class, then you can have a one number here because it is a classified image. And then with the class, you can store that number with the how many counts, and then what is that map, or field trees or crops and other things. You can depict that, or you can store that in the value attribute table. There is known called as a VAT. So if you see here the VAT, the value attribute table, this is value attributable for the raster data set only. And the examples are the land use class, soil with the code. So generally you give the soils with the code, and land use land class as a different codes for that. There's like a clay, loamy, sandy loamy, or black soils, and so on. Land use class, the forest, then built up area, rivers, water bodies, agriculture, horticulture, forest, all those classes can be then given a number, and then number can be then mapped with the attribute informations. The characteristics. It's very simple grid structures. That means it's just consider the only rows and columns, just like in our Excel. If you see the Excel, it also consists of the rows and columns exactly the same way. You can create your own image in the Excel also, just like in the images or in your photographs. The same thing can be, you can visualize those in the Excel also. So it is a simple grid structure of rows and columns. And then same thing is the pixels, and the resolution is based on the your cell size. Now what you see is the cell size is your grid, and you might be knowing the megapixels or so on. So those are nothing but your the how many pixels are there in per square inch. That gives the depth of your resolution and the clarity in your images. And the feature are considered homogeneous. Within that cell, within that cells, only one value can be accommodated. You cannot accommodate another value. So it is homogeneous in the within the pixels. So it can have a 5 meter, 5 also. So those cell size is nothing but the length of a one individual unit of cell. And storage increases with the number of pixels and the size of your resolutions. If it is a fine resolution, the storage of the images will be higher. The TIN data structure, the triangulated irregular network, or digital elevation model, or DSM or DTM. So those are nothing but a continuous data to represent your elevation information of the earth. You can see here a TIN is used to represent three-dimensional objects, and each point with the X, Y, and Z values to form the triangles. And this triangular mosaic forms the surface like a prism. If you see here some kind of prism, you can see here prism. So high elevations is to be on higher sides and then drop those things. So each point stores X, Y, Z value in the form of triangles, and it becomes triangulated irregular network. And examples are the digital elevation model or digital surface model. It can also represent for the evaporation, rainfall, or temperature, and so on. So if you see here relief, you can see, and the copy of translations, the higher the value, the more brightness. So here the copy of translation is more, and the dark spot, the copy of translation is less. So brighter the value, higher the value. Darker the value, lower the, darker the pixel, lower the value. And likewise. So there are many demerits also and merit of data, raster data. It is a simple data structure of rows and columns, and compatibility with the remote sensing and scan image. Then simply the spatial analysis is very simple with these things, and you can continuous phenomena like climate change modelings or hydrological modelings. These modelings require the data in the form of your raster. So if you heard about the SWAT model or Mike-Shi model or Haycross model, all these models require the data in the form of raster, and they take the raster data into their modeling systems and then does all the calculation of your water balance or your climate change scenarios. Then there are a variety of satellites that are readily available, like a high, medium, and coarse. So those are now readily available. So need not to again produce it. Some demerits are it requires greater storage space, because as I said, this images or the raster data is in the form of square and rectangle shapes. But in reality, our objects are never in the form of square or rectangle shape. They are irregular shapes. So what happened to the remaining portion of the circle? So I just would like to draw a few things. This is our image, but actual feature is this much only. Then you have a data here and you don't have a data here. Even if there is no data, then it will assume a no data in these portions. This portion will have a no data, because our real world locations or real world scenario, this is where the actual data is present and this data is not present. So these no data are available in the raster data set, and therefore it occupies more space because it has to be in rectangular form or square form. So it depends on the graph here. So it's always depend on the pixel size. If you have a very good resolution, then only you can have very good pleasant or good visualization of that area. And projection transformation are difficult because many times you cannot measure the areas and length and perimeters using the coordinate system of degree, minute, second. So you need to transform that degree, minute, seconds into the metric format, and therefore this, when you transform, then it's difficult in the raster data models, and more difficult to represent the topological relationships. Topological relationship is nothing but your relationship with the other objects, because in the real world these are all connected. A district road is always connected with your state highway, and the state highway always connected with the national highway. So that connectivity is maintained in the topological relationship. So maintaining the connectivity and then proximity is known as a topological relationship. Spatial analysis is more time consuming and therefore the processing also. Once you have the raster vector model, then you have another model called the non-spatial model. I told you there are the two things. One is spatial and then is the non-spatial. Under spatial, you can have a vector as well as raster. And non-spatial will have an attribute table, just like your DBase or your Excel, or in the form of text, or in the form of Oracle, or in the form of RDBS data. So what it indicates, the attribute tables. Attribute indicates the descriptions are of that objects. So description means what is that object, what it indicates, what it information provides. Suppose if you have a one weather stations, okay, you know that this is weather station, but what is that indicate weather stations? Whether it indicates rainfall, sunshine, temperature, relativity, or your wind speed, or many other parameters, and at what time series. So those can be answered using this attribute data and known as also descriptive data. So once you have a parcel like this, let's take the example of land parcel. These are land parcel, and that land parcel will have a buildings in it, and each building will have a different classification. You can see here, one here have the buildings, then feature class is building, and the building class you can have many classification of buildings like residential, commercial, industrial, multi-purpose, government, sports, education, service, transportation, and so on. So all those can be included into the attribute information and stored and link you to your spatial information. So this is all about the attribute informations. And apart from the tables, you can have images, photos, videos, hyperlink, and documents. Those can also be stored. Earlier, only these informations were stored in the form of a string or in the form of characters. But now, these days, images, photos, and videos, hyperlinks, and document can be saved as an attribute table with that feature. Now the map projections. So let's talk about the map. I told you we have a 3D feature of the Earth like this, and it is measure of latitude and longitude that gives your location on the Earth. But if you want to measure the length, if you want to measure the area, then it is not possible with the degree, minute, seconds. So what do you do? You flatten the Earth on a piece of paper, and a conversion or mathematical transformation of 3D dimension to the 2 dimension is the map projections. Now you can measure here the length, you can measure the area, and so on with these features, with these map projections. In the spherical feature, it is not possible. So this is a simple way, a map projection, conversion from the 3-dimensional to 2 dimensions to measure area and length of the Earth objects. And now, while doing so, when you convert from the 3-dimension to 2-dimension, there are many distortion happens, and these distortions are the distance, sometimes direction, sometimes scale, and sometimes area. We'll learn about those. Map wrap on the globe, just like a piece of paper. Now, if you have a line here, this projected line will be change in the distance. A polygon, then change in the size, and change in the shapes, and change in the directions. So all things happens when you do the map projections. So therefore, it is always advisable to use the appropriate map projections while converting your geographical projection to the metric or project. When it comes about the map projections, then you must know the datum and Spheriod also. So datum is the imagery lines where the coordinate systems are based on it, because on the above which all the calculations or the geometric calculations are built or measured and calculations were done. So most of the time, the WGS 84 datum, that is World Geodetic Survey. WGS is World Geodetic Survey 84 is the most common example of datum that is used globally. And all datums are based on some spheroid, because Earth is not a irregular fractions, but to give a dimension or give a calculations, a shape of the Earth has to be fixed. So there are different models which define the shape of the Earth, but one of the most important is the spheroid, where the spheroid have a semi-minor axis and the semi-minor axis. So major axis and minor axis, and therefore this, when you do the projection systems, it automatically takes your semi-major axis and semi-minor axis. The second most important map projection and most popular projection is the UTM, Universal Transfer Mercator projections. And these are very useful and mostly used for India. And you can see here what are the different UTM zone that India territory falls. So it starts from Gujarat, and the UTM zone is 42, 43, 44, 45, 46, and up to go to 47. So Maharashtra is in the 43 as well as 44. So if you are going towards Vidarbha side or doing some analysis or capturing some data, you should always project your coordinate system into UTM 44. Then you will have a accurate measurements of area and distance. So original projection is a geographical, and then transform into the Lambert conformal or Mercators or cylindricals or conicals. So these are the number of map projections available. You can use those map projections in the softwares. Now next comes the accuracy and resolutions. So accuracy says how well does database matches with the real world. That means how close with your real locations. So you will have a positional accuracy and accuracy of location as well as shape of the map features. And the second is a resolution. So resolution is nothing but the size of smallest features able to recognize a smallest unit. We generally term is the 5-meter resolution, 10-meter resolution satellite data. That means in that image on the ground, you can measure that unit. If we have a image of 10 meter, then you cannot measure the data on the ground less than 5 meter. It can go, it should be more than 10 meter. For raster data, it is a pixel size or cell size, and resolution plays a very large role in GIS, especially in raster-based modeling, because raster, once you have a fine resolution, or then your modeling will be much faster, but at the same time, it will take more time to process the images as well as do the modelings. Then there are different type of resolutions. We'll learn about those: spatial, temporal, high, medium, and coarse. Just now remember those things. We'll learn about those features. The spatial resolution is nothing but the smallest unit that can measure on the ground. Now you see here the 1 meter. In 1 meter, you can measure the corner of the building. You can measure the corner of the buildings. But in 3 meters, you hardly identify the corner. But you can say, this is the structures. This is the structures. This is some kind of a structure. Or can identify, yeah, this is a tree. Or identify this is a dome kind things. But when you go to the 10 meter, you hardly recognize the feature, but you still can recognize, yeah, there is some feature, man-made features like this, you can identify. So this is how the spatial resolution varies. So more fine resolutions, you will have more clarity. At the same time, the data processing will take much time. So it is always advisable to choose your spatial resolution in such a way that suits your project requirement or modeling. Now the map scales, a scale that describes the relationship between a single map unit to the number of same unit in the real world. And it is always in the fractional scale, that is 1:1000, 1:10,000, 1:50,000. That means 1 unit on the map is equal to 1000 unit on the ground. So likewise, if you have 1 centimeter in the map, on the ground, it will have a 1000 centimeter on the ground. And secondly, it can have a graphical scale like this one. You can have a graphical scale like this, where you can put your scale and measure the distance or area. Now, scale and resolutions. What is the difference between scale and resolutions? I will just give one small example to understand this. If you have a map of 6 lakh, it is the smallest one. Then if you have a map of 2 lakhs, a small scale. Then you have a map of 1:70,000. 1:20,000 larger scales, then 1:5,000, and then 1:500, very large. In all this scenario, if you see here, as your scale goes up means towards lesser side, very large scales, your resolutions increases. In general, 1:1000 is equivalent to 1 meter resolutions. So if you want to map the feature, or your project requirement says that we need a map of 1:1000 scale, then you must choose 1 meter resolutions. If you want to have a 1:10,000 scale, then 10 meter resolution you should choose. So likewise, it has to go. So if you want to have 1000, then choose 1 meter. If you want 10,000, then 10 meter. So likewise, it is general thumb rule. Here you can see here just a reservoir, a dot. Here also you can see some shape. Here you can see really a shape. Now you can identify the shape, and large scales you can identify the canal, rivers also, and you can identify the number of gates in the reservoir or dams, and the width of spill or width of the river also. So this is how it improves your accuracy of observations as your resolution goes up. At the same time, your scale also goes very fine, very large. So always it depends on your project requirement. First, you see your project requirement, whether you want a mapping in the scale of 1:1000 or 1:10,000 or 1:20,000 or 5,000 and so on. This is one example. This is given one example. A map scale and detectable size and raster resolution that you need to check. So on this side, you see here, it's large scales and small scales. A large scale maps typically shows a neighborhood, localized areas, small towns, and fine details, and small scale map shows a large geographical area. You must be confusing with your small scale and large scales, but this is how it terms in the GIS. A small scale is always very broader details. It is not really exactly small scale, but very large scales. So 1:1 lakh is a small scale map. 1:5,000 is a large scale map, and 1:1000 is very large scale map. So this is how it goes, small and large scales in the GIS. And this is just a one thumb rule where you can have 1:1000 mapping scale is required, then you must have resolution of 0.5 meter and so on. Now, what are the function of GIS? So GIS does many function like a digitization. It convert data, it scan and interpolate satellite data. Stored, retrieved, and produce a graphical analysis. It project the data, build the relationship with the spatial and non-spatial data, and so things. It create the topology. It maintain the relationship with your different object. It does the spatial analysis like clipping, overlay, near, buffer, intersect, extraction. These are some of the tools that is available in the GIS under the analysis tool. Building model with a vector and raster as per the project needs. You can create maps. You can share the map, print the maps. These are some of the file database, normal file database. These are available normally. First is the shape, then TEEN, and then ASCII. And these are known as the Open Geospatial Consortium, OGS. For raster, it is GeoTIFF, TIFF, ORI, or band interleaved pixel or band interleaved pixels, band sequential, KML and KMZ, key mark whole language, and so on. These are the open source, and these are the proprietorship developed by ESRI, like PGDB, personalized geodatabase, file geodatabase, coverage and info. And these are some DGN, Bentley Microstation, and ADAS Imagine. These are some of the micro, but mostly use those shapefile, TEEN, GeoTIFF, KML, and KMZ as an open source format, like Open Geospatial Consortium. There are different GIS softwares in the market. First is the ESRI, which is most popular. The next goes the Map Info. The third is Intergraph. The Bentley Systems is also there. And then ArcGIS desktop has two primary model like your ArcMap, ArcCatalog, ArcScene, and then ArcGlobe. ArcMap is to display map, produce analysis. ArcCatalog is like a file explorer where you can see your GIS file. And ArcScene is used for the creation of 3Ds. ArcGlobe is used for the 3D as well as the 3D calculations. It also comes with the different analysis extensions like a spatial analysis, 3D analysis, business analysis, network. So different applications have different extensions. Recently, the most open GIS software is the QGIS, Quantum GIS. It is open source and free. Anyone can download. Documentation learning material is free. It is constantly upgrading to new features and extensions. Many universities and international organizations are supporting. And due to this, the popularity of GIS is again increasing rapidly. Now everyone using GIS, or they have to use the GIS in their work or in their daily life. These are some of the different image processing software. That is satellite image processing software. ADAS Imagine that tops on the list. Then ER Mapper, then NV, PCI Geomatica, GRASS, and Elvis. That is on the Netherlands. These are some of the keywords. Data is information with the units like centimeter, kilometer, and all those things. Information, description of data or event. I think I will go fast now. Database, I have to cover the remote sensing. Spatial, which has a location, data. Non-spatial, vector, has magnitude, raster, point, line, polygon, and so on. So let us learn about some GPS concept. What are the GPS? Different components, concept, functions, data check, and quality control, and few applications. So you must be knowing this is a very handy Garmin handheld GPS. Many people might have used it or maybe using it. Juno or Garmin, these are the most popular. It is a system of satellites continuously moving around the Earth, 20,000 kilometers above the Earth's surface, to give the precise location on the Earth in degree minute seconds. So it gives a degree minute seconds. So it is provide the locations anywhere any weather. So this GPS works in any weather conditions, weather independent system. So if there is a cloud, if there is a storms, or if there is a cyclone, it will not affect those satellites and their observations. It measures the longitude, latitude, and elevation and the time. It has a two level. One is the standard position servicing, that is called the SPS for general civil purpose, and then one is called the precision position systems, primarily for the defense. So there are two systems, and these services are embedded into your device. So those device which has a standard position service will be enabled for the civil services. The precision position service is not available for the normal users in their devices. So GPS system is three components. One is a space component where the satellites are there above the Earth, which is 20,000 kilometers above the Earth's surface. Then you have a ground control segments, master stations, monitoring sections, and ground antennas where they turn, switch on, switch off, or change the rotation or change the orbit of the satellites, GPS satellites. And the third segment is the user segments where the devices we use and take the signals from those GPS to record the X, Y, Z and time. And these satellites, GPS satellites, carries two kind of band. One is called the L band and second is called the precise band that we'll learn about the next few type. And those travels at the speed of light. So using the speed of light, they calculate the time that comes and reflect back and record the time travels and measure the location of the time. Measure the location as well as time. So animal channel is produce a carrier phase. This is 575.42 megahertz, as well as it is known as a CA, coarse acquisitions, or P code. So those are all same. The second is a L2 channel produces carrier phase. So these are more precise, and it is a P code, that is a precise code. So GPS receiver calculate the distance using the speed of light and the time taken to reach to the device. Now here the space segment, if you see here, there are 24 to 30 satellites are always moves around the Earth orbits around 20,000 kilometers. Now, and they provide the user on the ground to 5 to 8 satellites. So they are positioned in such a way at any point on the Earth, you can see 5 to 8 satellites at that point. So they have designed in such a way that you can see at least 5 to 8 satellites to record the measurements. For computation of X, Y, Z and time, so minimum 4 satellites are required, but advisable is 5 and more. So control stations receive the ground signal from the satellites, which are converted into position and then time. And the user segment is our own systems where we use the our devices to measure the X, Y, Z. There are different type of GPS. One is called the handheld GPS, that is called the navigational GPS, carries the N1. Accuracy is less than 10 meter. Greater than 10 meter. Handheld GPS has less than greater than 10 meter. However, if you have a differential code DGPS, then it is less than 1 meter. If you have a carrier phase, that is a P channel, L2 channel, then it has a centimeter level accuracy in XYZ. There are various GPS system satellite available. Nowstar from the US, GLONASS from the Russian, and then Galileo from the European Union, and Chinese Compass navigation systems, and then recently Indian regional navigation satellites. NAVAC is also under constellations, and there are 7 to 8 satellites is already moving on our Indian regions to record the XY positions. GPS are used for navigations as well as position and geotagging of water resource assets, ground truthing of the crops and land use, and so on. And more costly GPS, it is more expensive. So it is always comes with the cost, but it's mostly used is your handheld GPS. And in your mobile also, it uses the GPS receiver, which is having coarse signals and then take the greater than 10-meter accuracy. So best in the market is the Garmin, Itrax, or Trimble Juno. These are some of the checklists that you should check before going to the recording the measurements, degree minutes used, datums, and minimum number of satellites, 4 or more, and PDP should be your less than 2. That is your, see here the distribution of your satellite should be uniform. They are at one place. So more very uniform distribution will yield a very good result. There is one more GPS called the DGPS. That is a differential GPS. It increases your accuracy of more measurements in XYZ. And these works in the two system. One is a receiver and called the base and the rover. So base is fixed at a particular point for 24 hours, and the rover used to go move around and take the measurements. And using the reference from the base stations, the difference is transmitted to the base rover, and the difference is added to the recorded measurements to have accurate measurements. So this is why the differential GPS. So it records the difference and then send it to the rover for accurate measurements. So this is, thank you. I will just switch over. Meantime, if you ask me, okay, otherwise I will start. Second presentations, I will stop sharing first. Okay, I will take a 1 or 2 minutes a break. You can ask me question. Okay, if you have any on this or queries.
Participants, if you have any question, you can ask directly to the sir. I unmute yourself.
Okay. Otherwise, I will go to the remote sensing part. 2 minutes.
I think no any questions, sir.
Okay. So
we can start the remote sensing part.
Okay. I will share my presentations. Sorry, actually, I had a cough, and that is the reason
Okay, you can continue.
Drink a lot of water. Actually, I was sick.
Actually, these topics are new to UG students.
Okay.
One course is there, Geoinformatics, Nanotechnology, and Precision Farming.
Mm-hmm. Okay.
In that, in the fifth reading, they included this syllabus.
Yes. Now, yeah, these people and these participant and student can learn now. It's a good time.
Yes.
We learn these 5 years after graduation.
I'm also after PhD.
Okay, so that's okay now. People are learning in the graduation now only in the syllabus.
This is need of our.
Yes, right. So shall we start the remote sensing part now?
Yes, sir. Yes, please proceed.
Okay. Hope the slides are visible.
Yeah.
Okay. So let's go about the remote sensing. Some basic concept of remote sensing is it's a science as well as art, because science is it gives how it is to be captured without touching that object. And secondly, art is how it represent in the picture, in the image. So that is art. So it is a combination of both science and art of acquiring information or about analysis and making analysis of that object without physically coming in contact. And then most common example are our cameras. Even our eyes are also remote sensing, and satellites, radar, LiDAR, X-ray machines. These are all the remote sensing, comes under remote sensing sector. However, in the natural resource management or in the agriculture or in the land and water management, our systems is different. We depend on the sun, and then we have earth, various objects like forest, water, bare soil, paved and buildings, and we receive continuously the sunlight, and those are called the incident solar radiations. They fall on these objects, and then they also have a property to reflect back. The forest, forest reflects some amount of energy, water reflects some amount of energy, some amount of energy they absorb also. So there is a three process happens. One is the absorptions, and some is the diffuse. So those three things happen simultaneously: bare soil and paved and buildings. So those are called the reflected solar radiations. So one time is a incident solar radiation and reflected solar radiations. And then in between there is the atmosphere. So reflected radiations has to go back to the satellite through atmosphere, and satellite record the measurement of those different different reflected solar radiations. And this is how the satellite captured. Satellite doesn't capture, but the sensors on the satellites. Sensor capture the reflected solar radiations and record the measurements. Record the measurement in terms of the some units, and these units forms in a special fashion called a raster, and then they store the data in different form. Now, when the incident solar radiations comes, it comes with the electromagnetic spectrums. However, in the remote sensing, we mostly deal with the visible and near visible or infrared. So our visible range starts with the 0.4 to 0.7 micrometer. This is the visible range. We'll know about this thing in few further slides. So this is how the solar radiations, reflected solar radiations, been captured by your satellites. Now there are two types of remote sensing satellites. One is called the passive. Now passive use its own solar radiations. A passive use the solar radiations, and then solar radiations then reflected back and acquired by the satellite. And there are different satellites: ResoSat, Landsat, and Sentinel. In active or synthetic aperture radar, it's called they have own source of energy. They incident. That means they use their own source of what is happening. They use their own source of energy. Here sun is not used in SAR, and therefore this SAR is known as radio detection and ranging radar, or light detection and ranging LiDAR. So these are the two active remote sensing satellites, and these are ReSat. One remote sensing satellite ReSat is under utilizations, and which is a microwave satellite. These are also sometimes called the microwave satellites, and these are called passive satellites. So passive use their own natural source of energy, where active use its own source. So type of satellites, one is geostationary satellites, which is known as a meteorological or communication satellites. Those are placed around 36,000 above the Earth's surface, and therefore they are more, they can capture more area. And sun synchronous satellites or polar satellites, known as a remote sensing satellite or GPS satellites. So they move around the polars of the Earth, and they, in geostationary, they use the equator to move. So they are traveling along the rotation of the Earth, and here it uses the solar directions. So as the sun rotate, then it also changes the satellite positions. And they are placed around 600 to 1,700 kilometers from the Earth's surface. So remember, the geostationary satellites are always placed on above 36,000. However, sun synchronous or polar satellites or remote sensing satellites are around 600 to 1,700 kilometers from the Earth's surface. When it go to the atmosphere and recorded by, what happens? What happened with the reflected radiation from the Earth object? It get absorbed. The reflected radiation get absorbed by the water molecules or ozone molecules or oxygen molecules, and therefore second is a scattering. The scattering light is also absorbed because of the various atmospheric molecules and particles. Therefore, the reflectance that is measured at the sensor level from the different objects like a forest, water and air and soil and buildings is different. And this reflectance is a ratio of your reflected radiations by incident radiations. So incident, it's just a simple ratio, and this ratio is stored as a DN number or digital number. And when you want to convert that digital number into the reflectance, then you need atmospheric corrections because of these attenuations or because of these absorptions and scatterings. To get the reflectance, the satellite's metadata is always provided with some calibration coefficients. These calibration coefficients can be used to correct our digital number or convert that digital number into the reflectance. So just a few terminology, remote sensing terminology. Spatial resolution is the capacity of sensor to discriminate smallest object on the Earth. That means it is the smallest object that can capture by the sensor of satellites. So data with a 0.5 meter, data with the 0.5 meter, 5 meter, 10 meter, 25 meter, GSD or ground sampling distance. This is called the ground sampling distance or spatial resolutions. And you can see here the difference between the 25 meter resolutions, 5 meter and 1 meter. You can see the road here, but in this case, you cannot see the road as well. Spectral resolution, the spectral bandwidth with the imagery is taken. That means if you remember, the satellites record the measurement at different wavelength because the sunlight also produces a wavelength in a different bands, like a 0.4 to 0.7 micrometers. And the distinguish between the spectral band is known as the spectral resolutions. So there are various examples like a high spectral resolutions. That is, some bands, some satellites are having a more than 220 bands. That is known as a hyperspectral. Some are medium spectral resolution. Those are having only 3 to 15 band. These are called the multispectral. Ani, next is spectral resolution 1 meter, 1 band. That is a panchromatic band. It has having only one band, that is a 1 micro wavelength. Now you see here spectral image in the green, image in the red, and images in the NIR. You can see the differences of those different images in different bands. Is green band, red band, and NIR band. This green NIR band is nothing but a band of electromagnetic spectrums. So it starts with the blue, green, red, NIR, and SWAP. So those will just in next slides we will learn about those. The third is the radiometric resolutions. The radiometric resolution is nothing but to record the reflectance in different bytes or bits. Suppose if you have images of very high resolution as well as more information in it, or digital number is more. If that digital number is more, then you can have a very good image. You can see here 8 bits image, that is 256 numbers. You will have a very good image. And 1 bit, that is only 0 and 1 value, will have no information. It cannot carry the informations. And how it improves the visibility as well as readability of that image once you have a very good radiometric resolutions. 8-bit is good radiometric resolutions. The next is temporal resolution. Temporal means how many times a satellites can take the picture of same piece of land or same location. So number of revisit, a number of visit, a time between the first visit and second visit is the temporal resolutions. So high temporal resolution less than 24 or 3 meter, 3 days. Medium temporal resolution 4 to 16 days. And low temporal resolution is greater than 16 days. Now you can see here this May 2017 image, here November 2023 image, and December 2010. You can see here how you can distinguish what are the changes that has been occurred over a period of time in this piece of image. Here it has come, some body, water body, or some structure has come, and it disappeared. So likewise, it can be classified. So this is how it helps you to interpret images, analyze the images. The next is the same radiometric resolutions as well as brightness value. That pixel 0 to 255, that is what we said. And it comes with the DN number, digital number. Higher the value, more the brightness. Lower the value, less the brightness, and the darker pixels. Now darker pixel means the energy reflected is less. When the brightness is there, the reflected energy is more. So at this place in this box, the earth feature, whatever the earth features that is there, it is reflected more energy compared to these objects. We'll see those things in the next few slides. These are some of the terminology that various satellite data that comes, and then you must know a spatial resolution, or sometimes it is called instantaneous field of view, but nothing but your spatial resolution. So we have a least 4, least 3 AVIPS data less than 0.5 meter, 23.5 meter, and 56 meters. Spectral band. Now, if you see here spectral band, it is having a 3 band images, B2, B3, B4. So B2 is a green, red, and NIR. In the electromagnetic spectrums, B2, B3, B4 is green, red, and NIR. In least 4. Now least 3, if you see here, there is one more band, or the spectral bandwidth is added, is a SWAR, and that 1.55 to 1.7 micrometer, that is a short wave infrared. This is a near infrared. Similarly for these. Now swath width is nothing but a maximum width that camera of that least 4 can take the image. So at one time, this least 4 can capture 70 kilometer by 70 kilometer, and least 3 camera can capture at once 140 kilometer by 140 kilometer image. So one tile image is consist of 140 kilometer by 140 kilometer, and AVIPS is 740 kilometer by 740 kilometers. So if you make a relationship between your spatial resolution and SWAT, lesser the spatial resolutions, you have a less swath width. So, and if you have a higher spatial resolutions, 56 meter, you will have higher spatial width. So it can cover more area. Data continuations is nothing but the radiometric resolutions. Radiometric, it is data is available with the 10 bits. This is also available with the 10 bits, and this is also available with the 10 bits. Earlier, these data were available with the 8 bits data. So this just a spectral bandwidth, how it appears. Blue is 0.4 to 0.5, green is 0.5 to 0.6, 0.6 to 0.7 is red, and 0.7 to 0.8 is NIR, near infrared. 0.8 to 1.7 is short wave infrared. And when you have only one band image, then you will have 0.4 to 0.7 micrometer. So you will have a blue, green, red as a one band, and it is always a black and white. So if you see here 0.4 to 0.7, this is a one band. So you are losing the information of blue, green, red when you combine this complete band. But at the same time, it improves the other things. Oh, this is already covered it. Now I'll just talk about what are the different steps in the satellite image processing. Once you have received the images, then you need to do some pre-processing. There are some radiometric, geometric, and atmospheric corrections are required. Then image analysis and operations, some band and histogram resampling has to be done. The next is image enhancement, changing the color or brightness or enhancement using various techniques. Then image transformation, then you calculate some indices or some extract the informations. Then you go for the image classifications. Image classification is nothing but the classifying your entire data into a certain groups. And this classification can be done using two ways. This is a class of unsupervised and supervised. There are many other classification techniques are available, but the classic one is supervised and unsupervised. So this is just a flow diagram or flow of processing the satellite images. In image processing, pre-processing, you do radiometric correction, that is called the level 1, geometric correction level 2, where you correct some of the effects from the Earth rotation and curvatures, some altitude, orbital variation, and terrain related internal distortions also get corrected using the geometric corrections. Then misregistration, if there are some multi-spectral images are there, then some misregistration can be corrected using the geometric corrections. Then some map projection and datum transformation is also can be done in the geometric corrections. The observed image is not an exact replica of original image. Now here, what you see, a raw image from the satellites is not exactly the what you see after corrections, because some of the features are get distorted, or some of the features are get elongated, or some changes happens because of corrections, and those changes are unavoidable. You can't avoid those changes. Then what you do, image mosaicing, stitching two or more adjacent image, then image registration or rectifications, that means georeferencing of your images with your masters. Then georeferencing those images with the given GCP or ground control point. GCP is a ground control point in geographic projections. Okay, so image analysis and operations, we generally conduct the inspection of bands, resolution, resampling, and some histograms matching. We check how many number of bands are there, identify red, green, NIR, and square bands, check their spatial and radiometric resolutions, check their statistics and pyramids, histograms, and so on. So all those things we do in image analysis and operations, and then we compose it and stack those images into the useful product, and then we make the false color composite. This FCC is a false color composite, and second is a natural color composite. So you use of FCC. I will let you know about this FCC in next few slides. Please wait. Now, as you know, the satellite images record the measurements and stored as a DN value, and this DN value then is available in every pixels. Now, if you want to analyze the statistics of those DN in your image, then you produce your histograms. The histogram is nothing but the number of pixels that falls in particular DN value. So here, if you see here, the maximum pixels falls in the range of some say 50 or 60 here, and very less number of points are available in 10% reflectance. So this is how you can see the curve of the histogram and see the shape of the histogram also. It gives a statistics, a mean, maximum, standard deviations, and then second standard deviation, and also on. So those are available in histogram. Once you receive the images, then you do some corrections on those images. This correction is known as a georeferencing or rectifications and other things. These are done to fit your image, raw image, into your own coordinate systems or a map coordinate systems. So there are various image to map coordinate systems. Here, the images are changed with the help of coordinate systems. Now, if you see here, there are some coordinates are also already available. So use the paper coordinates and correct this image using the simple these available coordinates. This is image to map rectifications. Then image to image rectifications. In image to image rectifications, we transform one raw image with the help of another master image or reference image. So it is an image to image rectification. Then third is a GPS ground control, GPS rectification method, ground control point rectification method, where you take the ground control point on the images, and with the help of GPS or DGPS, you go to the field at that point and record the measurements in the XYZ. And then you come back to the office and then use recorded measurements at that point to correct your images. Why this correction is required? Because of the Earth rotation and Earth curvatures and satellite misalignment, sometimes the satellite images that we received is not exactly of your same piece of land. It may be a displaced from your own project area or from your area of interest. So to bring back the raw image to the correct locations, we use the GPS, we use the control methods, we use the rectification method to correct the images. So while doing the georeferencing, fundamentally two things happens. One is a spatial interpolations. A spatial interpolation means a relocate. As I said, your raw images are displaced from your own images, area of interest. To bring back your location, then it needs to change your location. So this location change happens in the spatial interpolations. Then intensity interpolations. Now each cell will have a value in it that is called the DN or reflectance or brightness value. This brightness value also is going to change as we change the location of one pixel at different location. The intensity or the value of that brightness pixel also going to change. So change is known as the intensity interpolations. The changing the DN value is the intensity interpolations, and changing the location of the cell is the spatial interpolations. And these two things happens when you do the rectification. Then accuracy depends. Now, once you do the rectifications, then how accurate your images are. To check your accuracy, then there are different transformation models are available. And these transformation models are generally measure the accuracy in terms of root error or RMSE using different polynomial equations. You must have at least 3 GCP to do the first order. And because there are two, N1 and N2, and this is a formula where how many number of your GCPs are required. If you required only first order, you need only 3. If you put 1, then you will have a 3. If you have a second order, then you will have a more than 5. So likewise, it goes changing. The transformation accuracy normal computed as a root mean square error. And the thumb rule of this is the root mean square should always be less than half of your spatial resolutions. That means if you are correcting your 10-meter satellite data, then RMSE should be 5 or less than 5. These are available in any GIS and remote sensing softwares, georeferencing. These georeferencing automatically calculate the root mean square errors. And with the help of this RMSI value, you can ensure that your accuracy is good enough. Now, once you correct the image, then you need to enhance the image. For enhancing the image, you change some few things like you change the contrast of DN, and you change the spatial enhancement also. So contrast enhancement means it increase or decrease your brightness of image by changing the histogram. There is a facility in many of the softwares where you can change the histogram and see the visualization of those images. So those are known as a contrast enhancement. And these, some are the linear and some of the non-linear. So linear means a minimum and maximum will be accommodated into a fixed band. and non-linear means it will distribute it in a few groups and then it will be shown to the images. The spatial enhancement is nothing but it is nothing but enhancing the quality of interpretations. Sometimes you see the sharp edge or smooth or curves and all those things. And these spatial enhancement help us to improve the readability of the images. There are three types of spatial enhancement are available normally. One is the nearest, bilinear, and cubic. And these are also sometimes called the low pass as well as high pass filters. Here you can see the contrast enhancement FCC. Okay, I will just tell you about the FCC here. FCC means false color composite. Now it is also called the pseudo display. It is also called the pseudo display. Our computer can read and store only red, green, and blue. However, we have images in the band of NIR, red, and green. So arranging, that means NIR is given a red band is given G, and green band given a blue. We change the order. See here, the green should be green and red should be red, but we change just to visualize the images for better readability. Now here you can see the red or pink color. This red and pink color is nothing but the vegetations. And why this NIR is given red? Because vegetation reflectance in NIR is more than 40% compared to other band, and that's why you can see the the images like this. However, in the normal display RGB, you can simply give a red to the green, and then G to R and blue to NIR. Now you see here the blue as NIR, here red as a NIR. So this is a normal display. When you display images, then you are able to see these kind of images. Here you cannot make it, you cannot make any interpretation out of it. So likewise, then we change the color of those enhancements. So this is how we change the band and assign those color to the computer readable colors. Once you have a data and then enhancement is done, then what you do is sometimes you do the digitizations and then capture the various features. And then there are two types of digitization. One is manual digitizations, which is using the digitization table, and then but normally this is now been avoided and nobody is using it. This kind of tables were used to digitize the images. Now the recent one is the head-up or the on-screen digitizations. Now the most of the images are available in the digital formats. These images can directly display on the GIS or any remote sensing in software and can start digitizing using those features. Similarly, you can use the paper map, make it raster, and then start digitization using the table map. So these are also available. So digitization is nothing but a process of converting data, analog data or digital data into meaningful or a user readable formats. So you can pick up a land parcel, you can pick up a river, you can pick up a reservoir, and so on. This is just a data capture process where just mentioning the processes. Once you acquire the satellite image, you get the ground control points from the images, or do the GCP survey using DGPS. Then you rectify or georeferences your satellite images, check your accuracy, that is root mean square error. If you're satisfied, go for digitization or classification, whichever is the case. So that means once you have your georeference image with the accurate locations, then you can either start for the digitization or go for the classifications. And there are various classification methods are available: unsupervised, supervised, hybrid, and fuzzy. That will touch upon those things. First, I would like to know about the remote sensing sensors. So actually the sensors, these are the basic things. Actually, it should have been first. So what the sensor does, it records the radiation reflected from the Earth's features and transmit to the ground receiving stations. And in India, we have a master control facility at Hassan and Bhopal. So we have two facility at, one is at Hassan and second is Bhopal. Master control facility for remote sensing satellites are available at two places. One is at Hassan and second is at Bhopal. Hassan is near Hyderabad. And where did the radiation originate from? These are either from the solar energy or thermal or microwave energy or radar energy. So it's one is a natural source of energy, one is your own source of energy. So when you have one source of energy, then it is called the passive, and then it's called the active. And then passive is when you have a solar radiations. These are the number of satellites that is currently available in our Indian remote sensing region. This IRS is an Indian remote sensing satellite 1A, 1B, and they have a sensor like multispectral band and PAN. IRS 1C, 1D, these are now gone. I mean, these are not usable now. This IRS P6 is now operational. This was at 1. There's LEAS 3, one sensor is there. LEAS 4, AVIPs. LEAS 3 means linear imaging self-scanning. Linear imaging self-scanning. And this is advanced wide area field sensor. So it is a wide field, and PAN means panchromatic band. So it is a 23.5 and 5. Cartosat 2 and IRSP6, these are also under operations now. And recently, last week only, RISAT 2 was launched, which is again a microwave satellite, a radar satellites. And there are some remote sensing, few foreign satellites are also available. That is called the Sentinel, GI1, Worldview 2, Worldview 1, QuickBird, Iconos, and Spot. So this is already done. The most important is the spectral characteristic of the Earth object. So spectral signature of the Earth object is like this. That means a spectral characteristic curves means how the Earth feature like a soil, vegetation, and water behave with the electromagnetic waves, a different magnetic waves. Here you can see on the x-axis you have 0.4 micrometer to 2.6, and here reflectance. Reflectance is in the percentage. And this is I have to use the pen. This is for vegetation. And if you see vegetation in NIR band 0.7 to 1.7, 1.22 or something like that, the 50% reflectance is in NIR. High reflectance in NIR in entire regions. Therefore, this NIR band is used to distinguish vegetation from other objects. Okay. The second is water. And if you see the water here, the water absorb most of the energy and reflect only some 5% of the radiation in the green band. So total energy absorption by the water in all the band. And NIR, it is complete. For the soil, the reflectance increases with the increasing wavelength. The reflectance increases with the increasing wavelength. And the snow, it's very high in all the visible as well as NIR. NIR, it decreases rapidly. You can see here, this is the spectral band in pan image, 0.5 to 0.8. I'll show you one example. This red or pink color images. This is the vegetations. If you see the spectral characteristic curves, it should be like this for vegetation at this point. The reflectance is always greater than 40% in NIR for vegetation. For water, for dry soil, it always looks bright because the reflectance increases with the increasing reflectance. The third is water. Water appears dark because the reflectance is less than 5 to 10% in most of the band, in the green band, and NIR, it is almost absorbed. So this is the way of how you can distinguish or use different bands to distinguish different earth objects. Now, once you know the spectral characteristic curves, then with the help of spectral characteristic curves, you can go for the image transformations. A image transformation is nothing but the manipulation of multiple bands. Like if you have a band 1, band 2, then you can subtract it, add it, result. This gives a different perspective or enhancement. Just we'll see one example. Let's take the example of this vegetation index. Now here the main purpose is vegetation index. In this vegetation index, the NIR is used as to distinguish the vegetation because vegetation has very high reflectance in NIR band, and therefore the high value of vegetation. So vegetation index is a NIR divided by red band, and for water it is very low value. So vegetation will be white in this vegetation index. And IRS satellites has a band of 3 and 4 as NIR and red, and Sentinel 8 and 4. The normalized difference vegetation index. A normalized difference vegetation is nothing but the normalizations of NIR minus red divided by NIR plus red. This is negative for water and positive for value. Here the ratio is always -1 to +1, and you can see here the vegetation will always appear as a high, and NDVI value of greater than 0.2 will always a vegetations. Then third is a normalized difference water index. With the spectral characteristic curves, we saw that the green appears to be more reflective compared to other bands for water. So normalized difference water index use the green band and NIR to distinguish the water value, water objects. So this water value appears to be positive in this normalized difference water index and negative in the vegetation value. So it is a 3 and 4 and 3 and 8 values. So likewise, these different transformation can be used to characterize the various values. So NDI value is always from the -1 to +1, and plants always has a very high value, and therefore their value of NDVI is greater than 0.2. You can for water, NDI value is always approaching to the -1. For barren rocks and sands, always -1 to 0.1, and shrubs and grass 0.2 to 0.3, and temperate forest or vegetation, good vegetation is 0.2, 0.4, and very good vegetations is always approach go to the 0.6 to 0.8. So these are the some of the different things. Now just see the what is the NDVI and LAI. NDVI is normalized difference vegetation index, and LAI means leaf area index. So these are synonymous because as the NDVI increases, leaf area index also increases, where the crop productions used to be forecast. So for that time, they use the LAI, leaf area index, as compared to the NDVI. So these are just an example how the NDVI value correlated with the yield and how the NDVI value related to LAI. So NDVI value is most related with the LAI, not with the yield. There are different classification techniques that is to be used. One is the unsupervised classification, where you need to take some training samples. Unsupervised. For unsupervised, you don't need to take any training samples, and classes are automatically determined, and it does not require any prior knowledge also. It uses its own algorithm clustering methods to characterize the similar pixels and group into the one. The group represents the classes in the images, and the classes are obtained. And the most commonly known classification algorithms in the unsupervised is K-mean and ISO data. And there are mixed training, hybrid. It is performed combining both training data. Several techniques are used. Like sometimes you go for the unsupervised and then go for the supervised. So it's a hybrid or mixed training site. So use the supervised also. Supervised uses your own knowledge or your own classification or own ground truth sampling technique, and it applied two separate methods and combine the results. Then one more classification method is a descent tree, where the thresholds are used. Thresholds are used to distinguish from one from the other, and then go for the next, and then go for the next, and go for the next. So it is like a decision tree. So once it is classified, then it is ignored, and the rest of the things are treated as unclassified. That one treated, then the next unclassified will be treated for the classifications. Once you do the classification, then you have to sure about the accuracy. So classification accuracy is generally measured with the different objects. So it uses different shapes, directions, degree, and sometimes it uses the unsuitable classifications. And the most common methods are the visual, then the confusion or the fail matrix, confusion matrix or fail matrix, and second is a kappa coefficient. These are the indicator of accuracy of classification of satellite images. So confusion matrix is nothing but a diagonal accuracy, where you have a reference image here, ABC, and you have classified image ABC, and how many pixels are under A in reference image and in classifying image, and likewise the matrix is filled. And then classification, confusion matrix, overall classification is diagonally measured. So this is how diagonally measured. So this is sometimes called the omission user accuracy, and this is a commission producer accuracy, because this is a reference image and this is a classified image. So overall accuracy is 0.74, 37 plus 25 plus 43, and total number of sample is 142. So 102 divided by 142 is the overall accuracy of confusion matrix. This gives a how pixels are correctly classified. A more than 0.5 is said to be a good. More than 0.6 or 0.7 is said to be good. Then similarly, like a confusion matrix, you have another coefficient called the kappa coefficient to measure the accuracy of satellite image classifications. And it uses the two classified image as well as one is the reference image. there are only two agreements. One is the no agreement or perfect agreement. Here, the same, I am using the same example, and then kappa coefficients are determined using the diagonally. However, it uses the number of points falling into that particular classes also. So higher the kappa coefficient, more accurate the classification is. So better than 0.6 is always better. Kappa coefficient or confusion matrix, both. These are the some of the resource SAT1 and 2. These satellites are now available and the data is also available. This is Cartosat data. Cartosat satellites 1, 2, 2S and 3. Then availability of data that can be used. And these are the microwave satellites, RISAT-1 and RISAT-2 that is recently flown. These are the microwave satellites. Then scattermeter, this is for the ocean. This is the ocean, and this is for Indian remote sensing satellites for the natural resource management, and so on. And their applications are numerous. It can apply to the various agriculture for the crop acreage productions, remote-based crop yield estimations, as well as crop condition assessment, drought assessment, land degradation. It is used for the land degradations, soil affected soils, land cover, land use, land cover classifications, urban growth, urban sprawl, and for different environmental purposes like a forest cover mapping, green cover mapping, forest fire, biodiversity, and environmental impact assessment. So number of applications is very wide, and these applications is now currently using in different projects of the governments, various government sectors and their departments are using these satellite images and GIS to map, analyze, and produce and monitor those things, their projects and programs. For water resource, you can map the surface water following, flood mapping, flood zone risk assessment. You can runoff estimations, sedimentations, some geoscience on ocean applications also you can go. Some climate studies can be done like climate, atmosphere constituents, aerosols, and some watersheds also can be used. This is all from my side. That's all. I had to rush it actually. There are so many things. And thank you very much.
Okay, sir, no problem. If a participant having any query or question, they can ask.
From the participant side, if anybody having any query regarding the topic, you can ask freely. Lokesh. As the topic is new to all,
whether it is
this time,
I'm sure it may not have been understood, but still they can ask any question also. Even if it is silly or very silly, that is also okay. Asking a question, asking a question is the first thing to get out of this fear or some type of what to us or what not to us.
Until and unless they read any conceptual book, and then they will ask. No topic too much information.
Or it might be possible that this is too much for them. It's just the information that may be, but they could have done things and then. Yes, please. I will share that PPT.
Okay, Mr. Gule, if there are no any questions, you can conclude the session.
Yes, sir. So we are very much thankful to you, sir, on behalf of Department of Agriculture Extension and Communication, PGI MPKV Rahuri. Sir, you have very nicely elaborated all things regarding to the topic. Actually, it is a technical subject. Even so, you have taught it by very simple manner. In that, you have explained geoinformatics, what is GIS, factors leading to GIS, components of GIS, basic concepts of GIS, and that also basic concepts of two spatial model, raster and vector data model, and then a raster data model, basic concepts of non-spatial model and their attributes, then map rejection, accuracy and resolutions, and also GPS and its application. And the main important thing, that is the remote sensing, different technologies in that, or in terminologies like spatial resolution, spectral resolution, radiometric resolution, then raster and satellite images, its basic concept, images histogram, then images rectification methods, georeferencing of raster, then remote sensing sensors, accuracy, and important thing again, applications of remote sensing in agriculture and abroad. So thank you so much once again, sir, for giving
Thank
your
you.
valuable and knowledgeable guidance and spend your valuable time with us. Thank you so much, sir.
Okay, thank you.
Thank you, sir. Thank you.
Thank you. Bye.
Shall we conclude the session, sir?
Yes. I am going to end the meeting.